This is a long section. There's a lot going on. There's 13 pages to this section. And I'm going to try to blow through as much of it as I can today because we have to hit a section a day to get done on time. And in fact, we actually have to do 2 sections in one day so we can give you a test unless you all want the test in the testing center. I personally don't care. But if we need to hit a section a day now. In fact, there's one day I'm going to have to hit 2 sections in one day because I still have to have a test and one more test. Unless you want the test in the testing center, and I can put the next test in the testing center, you can take it at your convenience that last week of class.
Ooh.
Yeah.
You're all okay with that?
Wait, for what test?
Test chapter 4 test. So chapter 4 test option A is we still have to blow through these one a day. But if we have the test in class for chapter 4, we'll have to actually do 2 sections in one day, which will be delicious. Test in the testing center that last week? Okay. Okay. So this is a lot going on in this section, but it's not necessarily things we haven't seen already. So the first thing is the increasing and decreasing. We have seen this both in pre-calc 1, we've seen it in pre-calc 2, and then if you watch the video from yesterday, we define it the way we do in calculus. So we have increasing and decreasing. The other thing that's going to help us decide whether or not we're increasing or decreasing is taking the derivative. If we take the derivative of our function, that'll tell us whether or not we're increasing and decreasing. So I take the derivative and then I put a number in on one side or the other of the test point. So positive derivatives means that we are increasing, negative derivatives means that we are decreasing. So the first thing we've got is Theorem 4.1, which is the test for intervals of increasing and decreasing. So basically you just take the derivative and determine whether or not it is increasing or decreasing by doing a sine graph. So if you look at tomorrow's video from yesterday that I uploaded, if you look at the very last part of it, it's an increasing, decreasing. It goes over a couple of examples. So if I'm asked to find a graph that is continuous and then it has these conditions, f prime is larger than 0, so that tells me this f prime is larger than 0. This tells me I am increasing on those intervals. So I build any graph that I want, provided between negative infinity and 0, I am increasing. From 4 to 6, I am increasing. And then from 6 to infinity, I'm also increasing. So I have to be going uphill in this area. So my graph would look something like this. So I'm going uphill up to here, and then I am starting to not increase. Then I need to decrease somewhere here until I get to 4, and then I need to increase. Now, if you notice that my increasing is increasing from 4 to 6 and 6 to infinity. So right there, because I am butted up against each other but non-inclusive, that tells me I have a horizontal slide. So at 6, I'm going to have a horizontal slide, and then I'm going to continue up. So the graph may look something like that. Your graph may look something slightly different, but that's what my graph is going to look like. Yes?
Could between 0 and 4 also be a horizontal slide?
Between 0 and 4, yeah, it could be also a horizontal slide. It could be just constant. But it is definitely not increasing. It's not going up the hill. Okay? So the next one, if I'm asked for f prime is less than 0 on this interval, so I draw my graph, and between 0 and 4, I am decreasing. And I know I'm decreasing because my function is less than 0. The derivative of my function is less than 0. So I'm going to have some graph that may be increasing like this, and then I get to 0 and I decrease until I get to 4, and then I increase again. So it may be something like that. Now, could it be that it is horizontal in either direction before and after? Absolutely. But what I do know is in that interval between 0 and 4, I need to be decreasing. If it is a negative infinity, that means I am decreasing. What do you think C is telling me? No, it has to be continuous. So what is C telling me? It's a corner. It's either a corner or it's a vertical slide. So C is telling me that I have a corner or a vertical at x equals 0. So that's what that's telling me. So I draw a graph that either has a corner there, like an absolute value function, or I would do it so it has like the cube root of x also has a vertical tangent line. What is this telling me? F prime of 4 and f prime of 6 are the same and they equal 0. What is that telling me? It's a turning point. Now, it doesn't have to necessarily be a maxima or a minima, but it is a turning point. So this is telling me I have a turning point. And what we call this in calculus is a critical point. Okay, so if it equals 0, that means it's a critical point. What's happening in between there, we don't know. Yes?
Does that mean there are critical points at both 4 and 6?
Yes. So at 4 and 6, we have a turning point, or we have a horizontal slide there. One of those. Okay. So as we take a look at this, here's an example in which the derivative is greater than, and you can see the derivative being greater than in this region here. I am going up the hill. In this region, my derivative is less than, so I'm going down the hill. My derivative is not defined at that point, so I know that it is a peak in a corner. It could have been a vertical slide. Here, my derivative is 0, so I have a turning point. It's a critical point. Here is also a place in which my derivative is equal to 0, and that is a horizontal slide. I have another place in which my derivative is equal to 0. Now in this region, my derivative is greater than 0, and less than 0. So increasing, increasing, and then decreasing. How are we doing? Turbo fast. Oh, and I'm sketchy as hell today. So pay attention to my numbers, because it's not going to work out well, I'm certain. Didn't work out well this morning, so it's probably not going to work out now. Okay. So if they're asking us to find the intervals of increasing and decreasing on from negative pi to pi, the first thing I'm going to do is do the derivative. So I'm going to do the derivative. So when I do the derivative, I have f prime of x is equal to, and I have 2 cosine x multiplied by negative sine x. Okay? So what I have then is negative 2 cosine x sine x. And I'm going to set this equal to 0 to see whether or not I have a critical point in that region. So I'm going to set this thing equal to 0. So negative 2 cosine x sine x is equal to 0. And so that tells me that either cosine x is equal to 0 or sine x is equal to 0, or both. I don't have to worry about the negative 2, it's just a multiplier. If I divided both sides by negative 2, I don't have to worry about it. What I'm using is I'm using this rule that says if I have a times b is equal to 0, then either a equals 0 or b equals 0. So that's what I'm using. So on the interval between pi, negative pi and pi, where is cosine x equal to 0?
Pi over 2.
Yep. Is that it? So negative pi over 2 and pi over 2. Where is sine x equal to 0? Pi? Negative pi, what else? 0. So I have 0, I have negative pi, and I have pi. The reason I need these is because I need to determine on my sine chart where I'm going to break up my sine chart. Do I have to worry about the endpoints, the negative pi and pi? No, I'm not going to worry about the endpoints. So I'm going to do my sine chart just like I learned back in pre-calc 1. This time I do need the negative 2. I'm going to do the cosine x. I'm going to do the sine x. Across the top here, I'm going to go from left to right. So I have x is equal to negative pi halves, x is equal to 0, and x is equal to pi halves. And those come from setting my derivative equal to 0 and solving. Now the interval I'm looking at is from negative pi to negative pi halves, non-inclusive, so that's interval. So I have to choose something in that interval. My next interval is negative pi halves to 0, 0 to pi halves, and then my last interval is pi halves to pi. So I need to choose something in those intervals. What do you all want to choose in the first interval? Something that's easy. So let's do negative 3 pi over 4. Is that okay? Negative 3 pi over 4? That's in that interval from negative pi to pi, negative pi halves. Negative 3/4 is in between negative 1 and negative 1/2. So let's choose x is equal to negative 3 pi over 4. Now, this is negative all the way across, so I don't have to really do anything with that one, but I do have to put the negative in there. When I'm taking the cosine of negative 3 pi over 4, and this is where we love our trig that we all forgot, negative 3 pi over 4 is in this quadrant. There's negative 3 pi over 4. Who's positive in that quadrant? Is sine or cosine positive in that quadrant? No, so we know that these are all negative. Since those are all negative, that means this interval is going to produce a negative, which means we are decreasing. So let's choose something between negative pi halves and 0. Where is negative pi halves and 0? Something in that interval.
Negative pi fourths.
So negative pi fourths. So I'm going to choose negative pi fourths. Now that angle is down here. Who's positive down there? Cosine. So cosine is positive, sine is negative, that's positive, so I am increasing. Because a negative times a negative is positive. So anytime I have an odd number of negatives, it is negative. Whenever I have an even number of negatives, it is positive. So now I'm going to choose something between 0 and pi halves. What do you all want to choose? So I'm going to choose pi over 4. That angle is in this quadrant. Who's positive? Everything. But I have a negative 2 in there, so that's going to give me a negative, so that means I'm decreasing. So then I put in something on the interval from pi halves to pi. What do you want to put in there? So x equals 3 pi over 4. 3 pi over 4 is in this quadrant. Who's positive? Sine. So it is negative and then positive. So this region is positive, so it is increasing. Okay? So that is an increasing. So now we're going to go back to what did they ask us for? So they asked us for the intervals of increasing and decreasing. So my intervals of increasing, to answer this now, my intervals of increasing are from negative pi halves to 0, pi halves to 0, and then again from pi over 2, comma pi. And I don't include that end point because we happen to know that end point would actually be a critical point, so I'm not going to include the end point. Intervals of increasing and decreasing never include the end points anyways. So I am decreasing from negative pi halves, or negative pi, to negative pi halves, and then I pick it up again at 0 to pi halves. How was that? All right, let's do one more example and then we'll keep moving on. We're going to do b here, so I'm going to do the derivative. And so the first thing I'm going to do is find my derivative, f prime of x. So that's going to give me 2x, the square root of x plus 5, and then plus 1/2 x plus 5 raised to the negative 1/2 multiplied by x squared. So I'm going to set this thing equal to 0. I'm just going to go over here and rewrite it. F prime of x is equal to 2x, the square root of x plus 5, plus 1/2 x plus 5 raised to the negative 1/2, and then x squared. I'm just going to rewrite it so I can work it on over here. So what I'm going to do is I'm going to set this equal to 0. So I get 2x square root of x plus 5 plus 1/2. I'm going to bring that square root down. X plus 5 times x squared is equal to 0. Now the reason I brought that x squared down is because I'm going to multiply everything by that x squared plus 5 so that it's out of the denominator. So I'm going to multiply this by the square root of x plus 5. I'm going to multiply this by the square root of x plus 5. And I'm going to multiply this by the square root of x plus 5. What that does for me is it takes 2x, and then I'm doing the square root of x plus 5 squared, so that's just going to be x plus 5. This x plus 5 and that x plus 5 cancels, and so I get x squared over 2 is equal to 0. Now, I don't like the 2 there, so I'm going to multiply everything by 2 as well. So I'm going to multiply this by 2, this by 2, and this by 2. And so I'm going to get 4x, x plus 5, plus x squared is equal to 0. Now I'm going to go ahead and distribute that 4x through, and so I'm going to get 4x squared plus 20x plus x squared is equal to 0. I'm going to go ahead and rearrange it and factor. I'm going to add my x squareds, so I end up with 5x squared plus 20x is equal to 0. Factoring out of 5x, I get x plus 4 is equal to 0. And so my two critical points are when x is equal to 0 and when x is equal to negative 4. Stop and let you all catch up. Because I'm not asked on any interval, it's not telling me an interval, that means it's on all real numbers. So that's the interval that they're asking me to do. And so I'm going to have, on my sine graph, I'm going to have 5x, and then x plus 4. And then across here, I'm going to have x is equal to 0. Oh, I should have negative 4 first. X is equal to negative 4. And x is equal to 0. These do need to go in order numerically. So the interval on the left is negative infinity to negative 4. Between is negative 4 to 0. And then on the right is 0 to infinity. All right, let's pick something on the left-hand side of negative 4. What do y'all want to pick? Because we're out of control. X equals negative 5. That's going to produce a negative here and negative here. That region is positive. So is that increasing or decreasing? Increasing. What do you want to pick between negative 4 and 0?
Negative 3.2.
Cool. Negative 3.2. So my first one is going to be negative. My second one is going to be positive. My region is what?
Decreasing.
Negative and decreasing. And what do you want me to pick on the right-hand side?
Positive 100.
Positive 100. Woo! So I put in a positive 100, and they're both positive. So what does that tell me?
It's increasing.
They're both increasing. Both positive, so it is increasing. So my answer is increasing from negative infinity to negative 4, union between 0 and infinity. I am decreasing from negative 4 to 0. Yes?
Do we not have to worry about the domain of the square root of x plus 4?
Yes, we do. So we come back over here, and what is the domain we actually have to worry about?
Negative 5.
So my domain on this one goes from negative 5 to infinity. Negative 5 is my lowest number. So I come back over here, and so I look at this. Do I actually get negative infinity to, oh yeah, I never back up my iPad. It's going to kill me later, I'm sure. It's pretty pissed off. Do you see that? It's coming like every 15 minutes or so. You haven't backed up in 17 weeks. Oh well, whatever.
My high score is like 52.
I'll get to it. I'll get to it this weekend. Whatever. Okay, so do I really truly have from negative infinity to 4? No. Where do I actually really start then? Negative 5. So negative 5. Now, I should have chose a number then which should have been like negative 4.5. Look, it's doing it again on me. Should have been negative 4.5.
Is negative 5 included? Because you do have a fraction as...
Oh, we do have a negative 5 is included in the original function. But when we do the intervals increasing and decreasing, we actually don't get to have a hard right. Yep, we don't get to include it. So it is negative 5. Look at that. It keeps telling me it doesn't like me right now. That's okay. Okay. Any questions on that? And thanks for reminding me about the domain of the original function. Okay, cool. All right. So, as we know, critical points don't always mean that we are going to get an extrema. Every time we have a horizontal slide, we get a critical point, but it is not an extrema. What the first derivative test is going to tell us whether or not that is actually an extrema or not. So when I find those critical points, in this case, I look at this, I have a critical point right here, and I have a critical point right here, and those two places I have critical points, but the horizontal slides. So we use something called the first derivative test, which is this. It says, if my signs change from increasing to decreasing, then I have an actual extrema there. So this is similar to what we would have seen in pre-calc 1, which said if I come in increasing and leave decreasing, then I have a maxima. If I come in decreasing and leave increasing, then I have a minima. So we still have the same similar type of definition. It's just now we define it in terms of our derivatives. Yes?
You're not guaranteed extrema though, right?
No, we are not guaranteed extrema. In fact, if you have the cube root, you're going to get a critical point, but you're not going to get an extrema because it's increasing the entire time. So what this is telling us, if we go back to our example right here, that if we look at our example, by that definition, because I'm coming in increasing and I'm leaving decreasing, that means right at this point, at x equals negative 4, what I have is a maxima. Okay? This is telling me, because I'm coming in decreasing and leaving increasing, that tells me that that x equals 0 is a minima by that definition. First derivative test gives us that extrema. It actually tells what our critical points, if they really are an increasing, decreasing maxima or minima. So that's what the first derivative test does for us. Oh, is that's the question.
So basically first derivative just tells you if it's increasing and decreasing. That's not
Yeah, so we use the first derivative test to determine whether or not our critical points are extrema. So I use the first derivative test to determine whether or not they are actually extrema or not. Maximas and minimas. And in this case, they were because they changed sign. If they would have been the same sign, like this graph down here, see how this is greater than and this is greater than? So even though I got a critical point at 0, at c sub 1, that because they're both increasing, that critical point is not an extrema. It's just a critical point. It's a horizontal slide, in fact. So that's what the first derivative test says. Hey, I can figure out whether or not I actually have extrema at those points by looking at the sign on either side of them, of the derivative. Okay?
And then it's from negative to a positive?
Yeah. So if I'm coming in negative and I leave positive, this is a minima. And if I come in positive and leave negative, this is a maxima.
If it doesn't change, it's just a horizontal?
Yeah, then that critical point is not an extrema. Yes?
If we were testing, let's say, a much smaller graph or a graph that had a much more restricted domain, well, if there was a horizontal slide, it couldn't be an absolute extrema, but it could be a local extrema, couldn't it?
So the question is, if it's a slide, it won't be an extrema at all, because it's just sliding and it's going up. Yeah. All right. So when we are doing the first derivative test, basically it's everything we've just done, which is you go ahead and you find the derivative. So I want you all to do A. I want you to find the derivative. I want you to determine on the interval that's given to you if you have any extrema on that interval. So go ahead and do the derivative and determine if you have an extrema on that interval. So on A, please do the derivative. Determine whether or not you have any extrema on that interval. Okay, so let's take a look at A. We did the derivative. What did you all get for the derivative f prime? Okay, so negative 2x minus 1, I set this thing equal to 0, so negative 2x minus 1 is equal to 0. So I get x is equal to negative 1/2, yeah?
Yeah.
Now this one I don't need a sine graph. And the reason I don't need a sine graph is because I only have 1 point. So I just have to choose something on the left side of negative 1 and something on the right side of negative 1. So if I choose something on the left side of negative 1, what do you want to choose on the left? Negative 3. If I put negative 3 into here, is that going to produce a positive or a negative? Let's choose something on the right side of negative 1/2. What do you all want to choose?
3.
So I put in 3. Is that going to produce a negative or a positive answer? So I'm coming in positive and I'm leaving negative. Do I have a maxima or a minima? So I have a maxima there. Now, we want to know whether or not we have absolutes. And so the way that I find whether or not any of these are absolutes is I have to check my endpoints. So I'm going to do f of negative 4. I'm going to do f of negative 1/2. I'm going to do f of 4 and determine which ones are my largest numbers and which ones are my smallest numbers. To the original function, yep, into the original function. So I put negative 4 into the original function, and I'm going to get negative 4 squared minus negative 4 plus 2, negative 1/2 squared minus negative 1/2 plus 2. My last one is negative 4 squared minus 4 plus 2. So when I put in a negative 4, you all have calculators. What gets kicked out? What is it, negative 10? When I put in negative 1/2, what gets kicked out? You all have calculators? I don't have a calculator.
5/4.
What is it, 5/4? Positive 5/4?
Yeah.
Thank you. And then if you put in a positive 4, what gets kicked out?
Negative 18.
Okay. So in that interval between negative 4 and 4, we have an absolute max of 5/4 at x equals negative 1/2. Now remember, when I'm looking at my endpoints, these are just endpoint extrema. So the negative 10 and the negative 18 are endpoint extrema. So endpoint extrema of negative 10 at x equals negative 4 and negative 18 at x equals 4. And that's your final answer for that.
What is coordinates instead of doing negative 10 and x equals negative 4?
No. So if you give me coordinates for your maximum and minimum, I'm taking off 1,000 points.
That's for him. That's for him. Right?
Yeah, I'm gonna send you back to pre-calc 1. Get nothing from this class. You don't give them as ordered pairs. And the reason is because more often than not, the reason we do this is actually to do applications of this. And if somebody were asking me if it's a business application and they ask me where my profit is, I'm not going to say, oh, it's at negative 1/2 comma 5/4. Nobody's going to say that to you. They're going to say, after I've sold this many items, my maximum profit was. Okay, so there's a reason why we don't do them as ordered pairs. It is because they're real applications, and finding derivatives is delicious, but really we want to know why we do it, and that's the applications. Okay, so, and I'll do some of these other ones here on a video this weekend, so there's more examples. We do have to keep moving. Our theorem 4.1 guarantees that we'll have absolute values only if it is a closed interval. So can we have absolutes when it's not closed? We can have absolutes, but we're not necessarily guaranteed absolutes if it's on a closed interval. So, or on an open interval. So we have an open interval, we're not guaranteed absolutes. Okay? So, oh, look at that. You all want to do that example to verify that has an absolute extreme, or you want me to do the video on it?
Video.
Okay, cool. Now, the second thing that we do is the second derivatives. The reason we like doing second derivatives is because if it's an application and we're talking about distance being our original function, our first derivative is velocity, second is acceleration, third is jerk. But what the second derivative gives us in general is the point of inflection. It is the point in which we go from concave up to concave down. So when we do our second derivative and set it equal to 0, that means we have concave up and concave down. So if I were to look at x to the third, we know that x to the third doesn't really have, it has a critical point at 0, but it's not a maxima or a minima. So if I look at x to the third, here's x to the third. If I do the derivative of this, I'm going to get 3x squared. I'm going to set that equal to 0, and I'm going to get a critical point at x equals 0, which I test it and I see that it's increasing the entire time. But if I do the second derivative, I'm going to get 6x, and I have a point of inflection, pi, point of inflection, at x equals 0. That means I am changing concavity. Now, the cubed graph looks something like this. Here's my horizontal slide right here, and I can see I'm changing concavity. I'm going from concave down to concave up. My point of inflection is found by doing the second derivative and setting it equal to 0, which leads us to the second derivative test. You're going to be ready for this? You do the second derivative, you set it equals 0, you do a sine graph. That's going to tell you if you're concave up or down. That's it. So if I am concave up, that means my slopes of the second derivative are positive. So when I do my sine graph and I do the second derivative sine graph, if it is a positive number, I'm concave up. If I am negative, then I am concave down. So concave up, it's like that, and concave down is like that.
So you take the second derivative and you see it equal to the sine graph.
Yep. Yep, yep. So concave up can be going downward, concave up. Concave up can be going upwards, concave up. So take a look at this. This is concave up and it is increasing. This is concave down, but I'm decreasing. I'm still concave up though. Concave down can be increasing and concave down could be decreasing. So if you do the second derivative and it's negative, and you did the first derivative and it was negative, then it's going to look like this. So if the first and second derivative are both negative in that region, then it is both decreasing and concave down. If your second derivative and your first derivative are both positive, then you're concave up and increasing. So this is f prime is greater than 0 and f double prime is greater than 0. This one is f prime is greater than 0, f double prime is less than 0. This one is f prime is less than 0, but f double prime is greater than 0. And this last one is f prime is less than 0 and f double prime is less than 0. Now, your critical points are not necessarily your points of inflection. In fact, typically they are not the same thing. I'll wait till you all have a chance to draw or do that.
That's describing what our original graph is going to look like.
Yep, this describes what our original graph looks like. So, here's some more examples. If my second derivative is positive, then we are concave up. If my second derivative is negative, we are concave down. So if it is continuous by definition and f changes from concavity, this is how we defined an inflection point. So if it changes in concavity, that means we have a point of inflection. Now just because we set our second derivative equal to 0 doesn't mean I'm guaranteed to have an inflection point. Just like I'm not guaranteed to have my critical points to be maxima or minima. So let's go through this one right here, and they're asked for the following functions: a concave up and concave down and any points of inflection. So I'm going to do the second derivatives, but first I have to do the first derivative. F prime of x is equal to 12x to the third minus 12x squared minus 12x, oh look at that, plus 12. That's pretty cool. Now, I'm going to take a moment and I'm going to determine from here, my first derivative test, where I have maxima or minima if I do an increasing, decreasing, so I can get a better view of what my concavity is doing. So I'm going to set this thing equal to 0. So I have 12x cubed minus 12x squared minus 12x plus 12 is equal to 0. Let's divide everything by 12. X cubed minus x squared minus x plus 1 is equal to 0. Can I factor this by grouping? Yes, thankfully we can. So let's factor this by grouping. Out of the first two terms, I can factor out an x squared, leaving me x minus 1. On the second two, I'm going to factor out a negative 1, leaving me x minus 1. So I get x squared minus 1 multiplied by x minus 1. So x minus 1, x plus 1, and since I have two x minus 1s, I'm going to write that as just squared. All right, so this is just the first derivative, and I'm using this to determine whether or not I'm increasing so I know which way to do my concavity. So I'm going to do my sine graph. I have x minus 1 squared, and I have x plus 1. And the way I'm going to look at this is I have a x equals negative 1, and I have an x equals 1. That comes from the positive and negative 1s. So my interval from negative infinity to negative 1, negative 1 to 1, 1 to infinity are my intervals. Choose something in the left region. What do you want to choose in the left region? Yes.
Shouldn't it be x squared minus 1, not x minus 1 squared?
X minus 1 squared?
Isn't it x squared minus 1 in the parentheses though?
Yeah, but it factors into the difference of squares. Sorry, I was skipping steps. Yeah, I am sketchy, but what happened here is this became the x minus 1, x plus 1 multiplied by x minus 1. Yeah, sorry, I skipped that step. I went through it, blowing through it fast. I apologize. So we cool then? And I am sketching. You do have to check me. What do you all want to pick on the left-hand side? Negative 2. Now we like this one because it's positive the entire time because it is squared. We love that. That's nice. So then we're really just checking the second one. If I put a negative 2 in the second one, is that positive or negative? So these two together, negative, so I'm decreasing. So that tells me that I'm going to be concave down. Okay, so it's either going to look like this in that region, or it's going to look like that in that region. Depends on what the second derivative tells me. Now I'm going to put in something between negative 1 and 1. What do you all want to choose? 0. So let's choose x equals 0. When I do x equals 0, this is going to be positive. That's positive, so this is increasing. So what that tells me is my graph is either going to look like that or like that in my second derivative, because it's going to be concave up or down, but it is increasing. So the last one, I'm going to put in something on the other side. Let's put in, what do you all want to put in?
600,000.
600,000. Going big or going home? Positive or negative? Positive. So this is increasing as well. So what does that tell me at 1? It's a horizontal slide. Can I still have a change in inflection? Absolutely. So it could look something like this, and I guess actually these could look something like this, and these could look something like this. So it just really depends on what happens on the second derivative. So let's go ahead and do the second derivative. Is it okay if I divide everything by 12 and do the second derivative of that? Because it's just a constant, right? You're all okay with that? So let's do the second derivative. Sketchy as I am, you all do the second derivative of that, please, and then tell me what you all get. Second derivative. So what do you all get when you get the second derivative? Does that factor? I don't know, does it factor? Does it factor?
Yeah.
Yes.
Take context clues for 500.
So 3x and x. I'm going to put a negative 1 here. I'm going to put a positive 1 here. That factors, right? Check my factoring skills. Does that give me, is that right? I got some no's and yeses. Love that.
Yeah, that was right.
We agree it's yes? Okay. I got some more vigorous head yesing, so x equals negative 1/3 and x equals 1. All right. So now I'm going to go over to my sine graph. I'm going to put it right next to my other one, so negative 1/3 and 1. So x equals negative 1/3 and x equals 1. And my had 3x plus 1, and then it was x minus 1, right? Yeah? Okay, so I need something in this interval between negative infinity and negative 1/3. What do you all want to choose? Negative 555. Because we can. Because we can. So when I put that number in, do I get positives or negatives?
Negatives.
So I get 2 negatives, right? Negative and negative. So that region is positive. That means I am concave up. So concave up, cup up. Okay. Something in this region between negative... I didn't even finish. Spoilers. Okay. I put in, you all are wild. So I put in 0 and I get a positive and a negative. So that's a negative so that we are concave down. So C down. Okay. Now, in this last region, what do you all want to pick? 7. Plus and plus and plus. So we are concave up. Now, let's bring this all together. Okay. So let's bring these together with a single derivative sine graph. And starting with the leftmost number, x equals negative 1. Then x equals negative 1/3, negative 1/3. And then x is equal to 1. Now at x equals negative 1, this is a critical point. At x equals 1, this is also a critical point. At x equals negative 1/3, make that better, negative 1/3, that is a point of inflection. So I have my f and f prime. So f prime of x. In the interval between negative infinity and negative 1, that was negative. And from negative infinity, from negative 1 to 1, that was positive. So this is the region here. Both of those two rectangles are from -1 to 1. So those will be both plus. And then on the other side of 1, from 1 to infinity, that was also plus. Let's take a look at the second derivative, f double prime of x. In the interval between -infinity and -1/3, that's in that region I just highlighted with green, it was positive, so this and this are both positive. Between -infinity and, between -1/3 and 1, it was negative. And then from 1 to infinity, it's positive. So what that means in terms of my graph is from -infinity, so this region right here, from -infinity to -1, I am decreasing, but I am concave up. So it's going to look something like that. From -infinity to, from -1 to -1/3, I am concave up and I am increasing. So concave up and increasing is going to look something like that possibly, or that's concave down. It's going to look something like that, so increasing and concave up. And then in the interval between -1/3 and 1, I am increasing but concave down, so that could look something like that. And then in my last region, I am positive on both the derivatives, so that means I am increasing and concave up. So it's going to probably look something like that. Now, what I'm going to do then is I am going to find out where these points are happening. So I'm going to look at f of -1, f of -1/3, and f of 1, so I can determine where these points are happening on the xy plane. So I'm going to go back to my equation, which was, and I'm just going to write it over here, 3x to the 4th minus 4x to the 3rd minus 6x squared plus 12x plus 1. The reason I'm going to do that is so that I can not have to keep going back and forth. So I'm going to put in -1, and so I'm going to get a +3, and then a +4, and then a -6, and a -12 plus 1, and I get -10. And then I have 3 times -1/3 to the 4th minus 4 multiplied by -1/3 cubed minus 6 multiplied by -1/3 squared plus 12 times -1/3 plus 1. And I get about -3.48 approximately. And then 3 multiplied by 1 minus 4 multiplied by 1 minus 6 multiplied by 1 plus 12 multiplied by 1 plus 1. And I get 9. So the ordered pairs that I have are -1, -10. And then I also have -1/3, comma at -3.48. And then the last one I get is 1, 9. Now, the -1, -10, that was a critical point. The -1/3, -3 and 4/8, -3.48, that was a point of an inflection. And then the 1, 9 was also a critical point. So, the graph, bringing all this together. So at -1, -10, not drawn to scale. And then at I should probably make this slightly bigger for the -1. So let's make this -1, negative 10. And then negative 1/3 and negative 3. So this is a critical point. This is a point of inflection. And then at 1, 9, make this kind of somewhat symmetric. 1, 9, here's 1 and here's 9. So I know that, going back to my shape, is that between negative infinity and negative 1, I am concave down and decreasing. From negative 1 to negative 1/3, I am concave up and increasing. Concave up and increasing. At negative 1 and 3, negative 3.48, I am concave down and decreasing. At 1, 9, I have a horizontal slide and I keep moving up. And the reason I know that's a horizontal slide is because if I go back to my graph here, right here, because I have positive on both sides, I'm increasing on both sides of 1, on the left side and the right side of 1. That tells me that is not a maxima or a minima, so that tells me that's a horizontal slide. So based on my graph, that this is my absolute minima, and it is all I have. I have no absolute maxima. In fact, I don't even have a maxima. So there's a graph based on derivatives.